filled everything out too and signed it, so no one's gonna come yell at me that I didn't check these things. So good job. Okay. Let's do 7.4. Integration by partial fractions. Here's the really good news in 7.4. There's almost no trig. Almost. I have to say almost. Almost. I'm talking like maybe 3% trig. And here's why it's almost. A little review. I've asked you a couple times to remember this. What'd you say?
Arctan.
Arctan. Inverse tan or arctan. This is the integral of this is inverse tan of x. We've seen it a couple times. I told you the first time that you want to memorize it. I think it was last time I proved to you why it was inverse tan. We actually did a trig sub to get there. That's about all the trig we're going to see today is this is going to come up. A little applause, thank you. A little applause. Other than that, it's lots of algebra. So if trig is a really hard part of calculus, then algebra sometimes is. But I think today's actually kind of refreshing. It's kind of nice algebra. We have to be a little organized, but we've had that all semester already. So we're going to do some algebra, not to mention some calculus. But the algebra will help. So on the top of page, what is this, 45? At the top of 7.4, my question is this pretty easy to integrate? This integral right here with these two fractions. I got one person nodding. How many people think they could integrate this without me reminding you what you need to do? Just show hands. You don't have to, you could even lie if you want. Well, not even half of us, I'm a little worried now. Okay, so those of you who aren't sure how to integrate this, someone want to tell me why not? What part of it? Why are you, what don't you know? What part confuses you? What don't you like? More than half of you weren't sure. If I gave this to you, I could have given this to you, if I was your Calc 1 teacher, I could have put this on the final even. You should have known it in Calc 1. So going back to your Calc 1 memory, what might you have tried here if you weren't sure what to do? Yeah, maybe a u substitution. These are both u sub problems. If we look at this integral, I would maybe do a u equals x minus 2. If we look at that one, I would do a u equals x minus 1. I would do two different u substitutions because there's two different terms. But we could do two different u subs. We talked about already this semester that you want to get a little bit quicker with doing what I call the reverse chain rule or the u sub in your head. Let's just do a little u sub for the first one. If u equals x minus 2, what's du?
dx.
Just 1 dx, right? So just this guy by itself would be the integral of 5 over u du. For those of you who don't recognize that, think of it like this. I'm really hoping you recognize this guy. More than the ones who already raised their hands. If you were one that was unsure, do you know how to integrate this? Integral of 1 over u is natural log of u. This would have been 5 times natural log of u plus c. I'm just doing the first term, by the way. And am I done?
No, you have to.
Put the u back in there. So 5 times natural log of x minus 2 plus c. That would have just been the answer to this portion. So now, we did the u sub. Can you go back up here and see how you can go straight from here to there? Yeah, think of the 5 as a constant, and then you have 1 over x minus 2. So whenever you have 1 over anything, okay, that's a little too vague. 1 over anything whose derivative is 1. It's just going to be the natural log of that when you integrate it. So because the derivative of this is 1, I can just swap out my du for my dx and nothing happened here. If the derivative was something else, then we would need another technique, and we'll see those as we go today. So if this one is 5 natural log of x minus 2, What's the next one?
Or natural log of x minus 1.
4 natural log of x minus 1. Make sure you put your absolute values around your arguments there. They need to be there, otherwise it's undefined. WebAssign will mark you wrong, I'll mark you wrong. So that's fairly easy to integrate once we recognize those are just natural logs in disguise there. Agreed? I call it mental U substitution. That's weird. Okay, let me erase this part. So we did that one. So then the question is, well, so that one was fairly easy. Some of us already knew how to do it. A couple of us had to see a U sub to see if it was doable. What if I asked you to do this? What would you try if I gave you that?
I'll try to
Factory.
factor, yeah.
We'll try to factor it and see if maybe it reduces or something. I don't think it does, so we could try factoring it. X plus 3, denominator factors. X minus 2, x minus 1. What'd you say?
You don't really do much with factors.
Yeah, I factored it, it looks different, but I still am not sure how to integrate it. Someone said U sub, I think I just heard. Was that you?
Oh,
No? I mean, I think that's a reasonable thing to try, is to try U sub. Because if I let U be the denominator, and du happens to be x plus 3 dx, life would be pretty good. Right, because the derivative would be hanging around, like I like to say. Let's try that. If we try u equals x squared minus 3x plus 2, what's du?
So that's
2x minus 3? Oh, bummer.
yes.
dx, thank you. And that doesn't help us because if it was x plus 3, I would know how to get rid of that, but I still, there's no way to substitute that in with what I have here. Everyone agree I'm kind of stuck? So I could not have put this problem on your Calc 1 final. It's not something you learned how to do in Calc 1, which is why we're going to learn partial fractions. But let me jog your memory on your algebra. Remember these two fractions over here? From this problem? If I wanted to add them, to combine them into one term, what would I need to do?
Kind of common denominator.
Get a common denominator, which would be what in this case?
X minus 2.
X minus 2?
And x minus
X squared
1.
minus 3x plus 2.
Ooh, he says x squared minus 3x plus 2. You're right. It's actually this expression times this expression, because these are not equivalent. Neither one of them divides into the other one. Imagine if x, for example, was 7. This would be a 5 and this would be a 6. So to get a common denominator, you'd multiply them together and get 30. So the common denominator is x minus 2 times x minus 1. So I would need to multiply this one by x minus 1 to get that common denominator. But if I put it on the denominator, reminding you of your algebra, I'd multiply on the top. Remember your algebra somewhere back in the far distant memory? And then I would do what with this one?
x minus 2 from the top and bottom.
X minus 2 on the top and the bottom. Just practicing adding fractions. Told you there was not a lot of trig today, now we're adding fractions. Okay, so my denominator is going to be x minus 1 times x minus 2. We'll multiply that out in a minute. That's going to be my denominator. The numerator, I just have to do this work now. I have to take 5 times this minus 4 times that and combine everything to get one giant fraction. I'm going to distribute 5x minus 5 minus 4x plus 8. The light bulbs went over your head, Brittany, I saw that. If I multiply out the bottom, I end up with this. And when I combine like terms, big surprise, I end up with x plus 3 over x squared minus 3x plus 2. Does that look familiar? I see a lot of you nodding and pointing over there. This problem over here that we just talked about, not knowing how to integrate, is equivalent to that one that we just did, that we know how to integrate. So the goal is to take what we call a rational expression, fancy word for a fraction, right? A rational expression where you've got a polynomial over a polynomial. The goal is to take something like this and figure out how to break it up into two smaller ones that we know how to integrate. But most of us, including myself, cannot look at this and tell how to get there. How the heck are you going to figure out that it's 5 and a minus 4 and so forth? Everyone see the problem? But that's the goal. The goal is to take this fraction here and turn it into 2 or maybe more fractions over here so we can integrate it. And that's what partial fractions is. Partial fractions is recognizing that, hey, I must have added something to get there. Let's break it back up and figure out what we added. Questions on the goal? Okay, so let's talk about how to get there. So actually, the idea, I don't know who came up with it first, so if somebody wanted to factor, whoever wanted to factor first, that actually is going to help because when you factor the denominator, notice those were our denominators over there. So factoring is definitely where you want to start. So this is actually a first step. Okay, we're going to factor, recognize that we must have had fractions with x minus 2's and x minus 1's in them. I want to make sure I follow all my notes and I don't get you lost here. I'm doing this problem down below. I want to make sure I don't skip over my notes. Okay, I'll come back. So I'm in the middle of the page here. I have some other prose here, but the very bottom is where I want you to write out showing you how to break this up. We'll come back up here in a minute to this other point I'm making. It's a sidetrack, which I don't like it. So everyone see what I'm talking about? The bottom says we're given x plus 3. If we're given this, I'm going to show you how to break it up down there. So I'm just going to write the fraction part without the integral because first we have to do all this algebra. So the first thing you want to do is to factor the denominator and separate it into factors. Factor that so that we can separate it into two fractions. And then the goal is to say, okay, this must be some number over one of my denominators plus some other number over my other denominator. So it's trying to achieve our goal. We have one messy fraction. We're trying to break it up into the sum of two smaller fractions. The problem is we don't know what A and B are. So that's what we need to do is figure out. Based on what we have over there, what's A? What's over the x minus 2 over there on the far board? 5, right? Let me put it over here. The number over the x minus 2, that's a 5. A is 5. What's B?
4.
Ooh, close.
-4.
-4. See how I put plus? So B must be -4. Well, the question is, how the heck are we going to find that? Oops, I wrote B. Not what I wanted to do. We just talked about, when we compared to the other problem, this must be 5, and this must be -4 to make it equal that original problem. So our goal is to figure out how to find that. That's the goal for all day today. Okay, before we go into how to do that, because there's a couple different techniques, and it's a little bit messy, of course, because it's calculus too. I want to go back up to the middle of the page where there's a few little reminders. First, I said, what's a rational function? A rational function is any polynomial divided by any other polynomial. Slightly above halfway, you guys see that? This is rational function. So this only works when you have rational functions. If you had those radicals like we had last time, radicals are not polynomials, so it wouldn't work. That's why we had to learn tricks up. Or if you had sines or cosines or e to the x's, those are not polynomials, so it doesn't work. They're always just gonna be polynomials. So that's a rational function. And then the real important thing is the degree of the numerator cannot be greater than the degree of the denominator, or the same for that matter. I wish I would have worded that backwards. In this case, the degree of the top here is 1. This is the first degree polynomial. This is the second degree polynomial. That's good news. As long as the top is smaller than the bottom, we're set. If the degree is the same or more, we have to do some more algebra to get it in the right format. So that's what that's saying. If we have a situation where the degree is greater than or the same, we have to do long division. And not all of you remember long division with polynomials. Some of you never learned long division with polynomials. So I have this little example. We're still going to finish this one in a little bit. So imagine if I had x cubed plus x over x minus 1. That's one of the situations where the degree of the top is higher than the bottom. Anytime the degree of the top is the same or more, you have to do long division first. And it's not going to warn you. You have to look for this on your own. So you'll be stuck in the middle of a problem, you won't know where to go. Partial fractions won't work if the top is higher. So we have to do long division. I'm going to remind you about long division from 4th grade first. You guys remember how to do that by hand? 4th grade? I think it was 4th grade. Maybe it was sooner, I don't know, nowadays when they teach you these things. I learned it in 4th grade, just the other day. Let's review that. 234 divided by 5.
4.
Doesn't
4?
24
The answer's
times?
4?
No,
Starting 4 minus 20.
So I'm starting with a 4 because I want to know what I multiply by 5 to get 2. Well, I can't get a 2. So I'm looking at this part, right? What do I multiply by 5 to get 23? You guys are totally right, by the way, but the process is the same with algebra, so I want to make sure I point that out. So we look and say, okay, I need to multiply by 4 to get 23, so I'm going to put the 4 right here. And then what do I do with that 4?
Subtract 20 from 23.
Where'd you get 20?
Gives
Multiply
5
by
times 4.
Ah, so we multiply these two, right? We multiply those two. You guys know how to do it, but I want to make sure you think about the steps. We multiply those, and then I will let you subtract. And we get 3, and then we bring down the 4. And then we get 6, because we're saying 5 times what will give me this. So that's 30. And we subtract again, and we get 4. Yeah, we could keep going and do decimals, but what would the answer be as a mixed number? So 5 goes in there, 46 and
4 times.
4/5, right? That 4/5. So it goes in 46 and 4/5 times. That would be our answer if we want to leave it as a mixed number. Remember that from somewhere? The 4/5 might have been like 6th grade. Probably went in nicely back in 4th grade. Okay, we're going to do the same thing with polynomials. It's all easy here. When you put polynomials in it, it's harder to organize it. Rule number 1 is to set up your long division, but when you write this polynomial here, actually both polynomials, make sure you have every power from the highest one down to the lowest one. So I have x cubed. There's no x squared here, so I'm going to put a placeholder there for it though. Because if I don't hold the places, it'd be like if I wrote 101 and just threw out the 0 in the middle and made it 11, it would mess it all up, right? So plus x, and then plus 0, because there's no constant term there either. So I have the highest power, 3, 2, 1, and constants. And I'm going to divide by, I don't have to add any zeros to this one. Okay there? Okay, so what? Yeah, I just look at the first part. What do I have to multiply by x to get x cubed? X squared. And since it's an x squared, I'm going to line it up over the x squared terms right here, so it's just 1x squared. So the reason it's x squared is I was asking myself, what do I multiply by x to get this? So it's x squared. Now I have to take this x squared times this whole thing. Times the whole thing. So when I take x squared times x, I get x cubed. And x squared times my minus 1, I get negative x squared. Now, technically, I need to subtract this. Some of you can just write subtraction and do it in your head. But be careful, a lot of you will start adding the negative, when you should be subtracting the negative. This part we've got, x cubed minus x cubed, those are gone. What happens here? I heard both, I think. I need one hand. What, Joseph, what'd you say? It should be positive x squared, because I have a minus and a negative. A lot of times what people do is they just change all the signs and then add. Oops, changed it in the wrong spot. And then add. Everyone agree it's going to be a positive 1x squared? Because I subtracted the negative. Easiest place to make a mistake is losing a sign there. Okay, now what? Yeah, bring down the next term. I need two terms because there's two terms here. X times what gives me x squared? X, so plus x. Again, multiply this x times the whole thing. So that's x squared minus x. And we're subtracting. So I get 2x. Because again, we change that to addition when we subtract the negative, right? Plus 0. Bring down the next one. X times 2 will give me 2x. So I put plus 2. And when I distribute that, I get 2x minus 2. And I have to subtract all that. So the answer is positive 2 down here, right?
Yeah.
So when I divide it, I have x squared plus x plus 2.
2 over x minus 7.
Beautiful. Plus 2 over x minus 1. Just like we did over here, right? 4 over 5 was our remainder. 2 over x minus 1 is what we have left here. So when we had this integral, this is the way it was written on the board, on the paper. If we had this integral, which we don't know how to integrate that rational function, what we've just done is rewritten that division as this expression. It's really saying, I'm going to put it above it, I want to integrate x squared plus x plus 2 over x minus 1 dx. That's the same thing in disguise. Can you integrate that? I got about 3 nods, I'm a little worried. Yes, we can integrate x squared?
Yeah.
How about x? Okay, good. 2? How about this guy? Yeah, what would that one be? He's pointing over here to what we did over there. 2 times the natural log of x minus 1? So we can totally integrate that. Yes, sir?
I just have one question. How did you get the polynomial on the inside of the log division?
So the polynomial on the inside is whatever was on the top, but it has to have a placeholder for every single power from 3 down to 0.
Okay, and that's
So-
why it's the 0x.
So this was the original polynomial, but I had to put the other ones in there. Otherwise, when you go to subtract, there's nothing to subtract it from. Things don't line up. So you have to always have those placeholders. So if it starts off that way meaning the degree of the top is the same or higher than the denominator, you have to start with long division. Once you do that, you might be able just to integrate it, which we just talked about. Or you might still be stuck at the end here with something that needs partial fractions. And there's at least one of those in your lab assignment, where you do all of this, and then you need to do this technique, which we haven't even talked about how to get there yet. So step 1 is to double check the degrees. And then once you have the numerator lower, we're going to use partial fractions where necessary. other questions up to here? Okay, so let's solve the mystery on how to find the A and the B. Okay. Of course, we have cases like we've had before. So now I'm on page 46. It's the same problem. It's not the same problem that we started with here. I'm gonna rewrite it again. Over here, we know the answer to 5 and negative 4, we already talked about it. We're gonna now discover how to get it. So we were integrating, I'm just rewriting the same problem again over here. And our first step was to factor the denominator. Go in here. And we said we wanted it to be some A times x minus 2. I'm leaving some spaces here on purpose. And B times x minus 1. Same order I have it in over there. Sometimes I switch those and I don't recognize. Okay, so the goal is to figure out how to find A and B. What we're going to do is the same thing we did earlier. We're going to get the common denominator so we can add these fractions. So what do I have to multiply this one by to get my common denominator? X minus 1. So I'm multiplying x minus 1 here and up here. And this one needs an x minus 2. And if I put it on the bottom, I've got to put it on the top. Do we agree that denominators now match? So if the denominators now match, I'm not really worried about them anymore. I need to make the numerators match now. So if I just look at the numerators now, on this side I have x plus 3. On this side, I'm going to actually write this out. I have x minus 1 times A and x minus 2 times B. See what I'm doing there? Once I finish doing this, it better equal x plus 3, right? That's the whole goal, make it equal x plus 3. And now we have two different methods on how to solve for it. One of them is right up above method 1, where we multiply this out and combine like terms. So the step that you have written there, we're going to multiply it out and combine like terms, and you'll see where it came from. So this will be ax minus a, when I distribute here, and bx minus 2b. Still x plus 3 over here. I haven't done anything over there. So right up above the box that says method 1, I have this written. Let me write it in the same order. What did I do to get that?
You combine that.
I combine like terms. They're real messy terms, I agree with you. But these are both x terms, ax plus bx. I'm going to add the a and the b to combine the x terms. And the negative a and the minus 2b, those are not x terms, those are constants. So I combine those two. So here's my x term, right here, and here's my constant term. We still don't know what a and b are. Can you see that, Evelyn, or no?
No,
Okay, I'll move up to the top of my next line. So method 1 is going to use a system of equations. It's going to force these two polynomials to be the same. What's my x term on this side of the equation? What's the x term? I don't want to have just x right here. What's the coefficient in front of it? 1. There's a 1 right here. 1x. Guess what a plus b better be? It better be 1. This a plus b better match this 1 over here if they're going to be equal. You see that? Matching the coefficients. So for method 1, we're going to set the coefficients equal. So for the x term, 1 better equal a plus b. Because 1 is my coefficient here, and a plus b is my coefficient over here. What's my constant term on the left? My constant over here on the left is 3. 3? So guess what all this has to be? 3. Because I want this to be 1x plus 3. 1x plus 3. So I need to write that down. I need 3 to equal negative a minus 2b. This is a system of equations. That you learned in Algebra 1 and Algebra 2. You probably saw it again in pre-calc. Probably showed up somewhere in calculus that you need to use it. How do I solve a system of equations?
Isolate one variable and solve for it.
We could isolate one variable, solve for it, and that's called the substitution method. Solve for one and plug it in and solve the other one. Substitution is one method. What's another method?
Can you just add those?
Add the two equations together. Substitution, I can't spell it. Substitution. How many I's in there? Or maybe not enough T's. Substitution. When you stand this close, it doesn't work right. There we go. Elimination. That's where you add the two equations together. I don't care which way you solve it, you'll get the same answer either way. I actually would do elimination in this case because it's already set up nicely for that. You see that if we add these two equations together, the a terms will go away. It's going to give you the same answer, so whichever way you prefer is fine. So I'm going to use elimination in this case. So if I use elimination and I add these two equations together, I end up with 4 equals, the a's are gone, negative b. I'm adding the two equations vertically. Did I lose anybody there? Can you solve that for b? I hope so. b equals negative 4. So now that I know what b is, how do I find a?
Plug in.
Plug in b where?
You can plug in
Either of them.
either one.
Either equation is fine. Choose the one you like better. I like the one that's less messy myself. I'm going to plug it in the first one. So 1 equals a plus negative 4. So when you solve for a equals 5. Added in 4 to both sides. What do I do with those?
You plug in for your A.
Yeah, then I can plug them back in here for my A and B to actually finish this problem. So remember, this problem was one that I did it in advance to show you how it worked out. But if we didn't know where it came from and we wanted to now evaluate it, my next step would be to write this integral as 5 over x minus 2 plus negative 4 over x minus 1 dx, and integrate each term separately, which is how we started today. Questions on that method 1? What I did and parts of it, where the pieces all came from? Yes, sir.
So you have like a plus b multiplied by x, but then when you solve you put in the system, you didn't put x.
Right, because I'm just setting up the coefficients, because I want this side to be 1x plus 3, right? I'm using too many pens at once here. I want it to be 1x plus 3. I already have the x is there, and the x is here. So I'm just matching up the coefficient here, it has to be a 1.
Oh, okay, makes sense.
You see, because the x is already sitting there waiting for me. So it's just the number in the front, the constants, that I'm worried about. See, it makes sense now? Your face telling me no. I get that 1x equals a plus bx, but then if I divide by x, it's gone, right? So it's just matching the like terms. Other comments or questions? So that's method one. Method one always works. Method two, which I left you a little space on the side of the paper, works sometimes. Most people prefer it, but you will run into cases where method two doesn't always work, so you're gonna have to understand method one as well. Method two is a quicker way to find your A and your B. I put my notes down over here. So method two, I left you a little space over to the right. Maybe you've already written over there, so you need to squeeze it in somewhere. So method two takes the line, the first line underneath the word numerators, and uses that. So once you still have to do that first step where you get a common denominator, but once we get to x plus 3, that's the equal, I'm going to put it in the middle here. Once we get to here, my description says it exploits the fact that we've created an identity. This has to be true for any x's. If x is 7, these two sides have to be equal. If x is 94, these two sides have to be equal. And that's kind of what we did over there. We forced them to be equal. We ignored the x, which made it a little uncomfortable. But if it's 1x and 1x, it'll be equal. So what we're going to do is plug in any x we want. If it's true for any x, let's just plug in any x we want. And I want to use x's that make terms go away. Is there any x that you would like to plug in there that would make something go away? 2. Ooh, maybe 1 or 2. I heard both. Let's do them separately. If I plug x equals 1 in here, this whole thing is 0. If I plug 2 in, that whole thing is 0. Let's do both. Let's let x equal 1 and plug that in. If x equals 1, we're going to just replace all my x's with 1s. 1 plus 3. I'm plugging it in here, but most of you will just not even write that term, because that's why we're plugging it in. It makes it 0, right? 1 minus 1a. 1 minus 2 over there. We agree that that term is 0 right there. So I end up with 4 equals what? A times negative 1? Look where we already are. We're already here. Right? We're already to that term. So if you solve for b, b equals negative 4. It's a shortcut that works lots of times, but not all the time. We'll see where it doesn't work later. Yes?
So it would also be if I put in 2 and cancel out the 2 in the right next to B.
Exactly. So my next step will be to plug 2 in for everything, and then I'll probably figure out what A is. So when you have nice linear factors like this, with things that aren't repeated factors, you can just plug in each letter that makes something go away, and it will always solve for your A and B. There are lots of exceptions to that, which is why we have to understand this method as well. I often, when I'm solving these, will do a combination of the two methods. Like maybe I'll do this for learn one letter, but then have to do a system of equations for the other one. It all kind of depends on the algebra mess you have there. So try plugging 2 in. I'm going to write it up here next. Take that same line. Take this same line right here now. Plug in x equals 2. Why don't you try it? I'll give you a minute to try it before I write it up there. Some of you have already done this probably. Much preferable to the system of equations, I agree. But it doesn't always work. So you can't just choose the easy one every time. It worked in this case. There's cases where it's not going to. There's sometimes you cannot avoid a system of equations. partial fractions is really an algebra trick so that you can do calculus. Really, all we're doing here, we haven't actually done the integration. We're just taking the fraction and working to break it up into two fractions. And then once we do that, now we'll go back and do the calculus portion. Questions there? Okay, let's go ahead and take our break here. When we come back, we'll talk about what happens when we've got factors that are repeated, or maybe we have things that don't factor as nicely. Of course it gets messier. Always does. We'll take a 10-minute break. There, we got sugar, caffeine, all the above. Whatever else we need. I don't even know if I want to know what all that is. Sometimes I ask for more information than I want, right? Okay, let's summarize a little bit of what we just did, because everything we've done has been what we call case one. And case one is when you have what's called distinct linear factors, meaning that once you factor your denominator, all of them are linear. Linear meaning, what'd you say? They're lines. The exponents on the x's are just ones, like x to the 1, x to the 1. They're equating to lines. And they're different. So that's what we just did with that one. That's the easiest case to work with. They're all linear and they're all different. That works out nicely. Once we have the other cases is when we have to start worrying about method 1 and method 2 not being as easy and so forth. So case 1 is when you have different linear factors. Case 2, which is the next example down, actually not an example, it's the next method, is when you have factors that are repeated. So now we have a linear factor, but it really shows up twice. It's x minus 1 squared. And your thought might be to write it as a over x minus 1 plus b over x minus 1. What'd you say?
Then that's just the common denominators are here.
The common denominator is just x minus 1, right? So how are you going to get an x minus 1 squared? See how the same technique we used before doesn't work here? So what we actually have to do is to write it as an x minus 1 and an x minus 1 squared. Because we don't know which fractions got combined to end up with that final one. Give you an example of what I mean. If I want to add 1/7 plus 1/49, always nice a little review. If I want to add those, what would I do? The common denominator, right? Multiply this one. I should have changed color. 7 over 7. You end up with 8 over 49. Right? 8 plus 1. So here is a fraction with a perfect square in the denominator that came from some 49s, but also some 7s. Right? So same idea here. There's a perfect square in the denominator. Some of them might be that perfect square, and some might just be the factor by itself. Kind of like my 49 and my 7. You see that? What do you think we would have had to do if this was cubed?
3 times.
3 times, exactly. We would have had to have x minus 1 to the first power, to the second power, and the third power. So you need to have every power from 1 up to however many you have. So if there were 5 of these, there'd be 5 different fractions, all with each one having an x higher power on that x minus 1. Yes?
So if you had like 30 different fractions, it would be A, B, and C.
Yes. We're going to get to one later that I think goes up to J. It's going to be fun. Just a little preview to keep you focused and waiting for that excitement. They're like flipping their pages like, where could that be? It's the last one. But we'll get there. We're not there yet. Yeah, so you just keep adding letters for how many fractions you need. Okay, so we're going to start with this. So what do I need to do then to find A and B? Common denominator, which in this case is x minus 1 squared. This one already has the common denominator, so I just need to multiply this one.
Yeah.
X minus 1 times x minus 1, squeezing it in there. That's similar to what I did here. From the earlier problem. What's my next step? Okay, distribute, but we're really just gonna look at the numerator, so you're right, we're gonna do both. At this point, because my denominators match, I'm just gonna write down the line I get from the numerators. And I may or may not distribute depending on which method I wanna use. This is what I get looking at the numerators only. Agreed? So we could do method one, which would require distributing and combining like terms, or we could do method two. Should we do it both ways? Yeah, no? Yeah, might as well, sounds like fun. Sebastian said yes for all of you. He wants to do it twice. Okay, so if I distribute ax minus a plus b, method one, doing method one here, I just want to put my x terms together and my constant terms together. So there's only one x term, it's ax. And then all of this, negative a plus b, is my constant term. Similar to the last one, what's the coefficient here? 1. It could have been a 5, could have been a 5x, whatever it is, this has to match this, right? So there's a 1x here, which tells you that a has to be 1. We've already got a right in front of us. A equals 1, there it is. This 1 has to equal that 1. Those are both my x terms. So a equals 1. But I also need, what's my other equation? Negative a plus b has to equal 2. The constant term here, has to equal the constant term here. Yeah? So now what? Yeah, plug in our 1. We've got a, might as well do that, we can find b. Negative 1 plus b equals 2. Add 1 to both sides, b will equal 3. So that tells me that the original fraction of x plus 2 over x minus 1 squared has to equal 1 over x minus 1 plus 3 over x minus 1 squared. Do my a and my b in there. Technique is the same. The setup's the thing that's different with this case, that you have to know to do all those powers from 1 up to 2 in this case, but if there were 3 of them, it'd be 1 up to 3 for the repeated factors. Questions there? Okay, my next example puts all of what we just did together and includes the calculus part. So my next example, example 2, here we are, over an hour in, hour and a half almost. On to example 2, has a nice, long, messy integral for us. Looks like this. It looks like an integral of 3x squared minus x minus 3 over, it's already factored for us, which is nice. Plus 1 times x squared. There's a couple things we want to look at before we get started. Guys good? Did I leave out something? No?
I was just wondering, like, after that, is that the answer to the question? So we would box that in?
Yeah, so this one wasn't even really a question, it was just to point out what to do in this case. If it had been an integral, we would have to now integrate that and keep going. So this was just, here's case 2. This is what you need to do to get a and b. That's why I'm now doing example 2, which will be the whole question. So first things first, you always want to check the exponents to make sure the degree of the numerator is not the same or higher than the denominator. Always. You forget that, you're gonna get stuck in the middle of a mess, and then you'll realize I should have looked at that earlier. What's the degree of the numerator?
Squared.
It's x squared. What about the denominator? It's cubed, right? Because I have x squared times another x. So that's good. The numerator's lower. So we don't have to do long division. At least we checked. Long division is not necessary. Everyone okay what I mean by no long division? Okay. Now I look at my factors. Are they linear? No? I think they are. One of them doesn't look linear. Was this a linear factor? This is a linear factor that happened to be repeated, right? X minus 1 times x minus 1. So, but it was linear, it just got repeated. What's x? X is linear, and it's repeated. X squared is the same as x times x. That's a repeated linear factor. What would be a nonlinear? What's a factor that wouldn't be linear, just so we know what we're looking for? We're going to do one of those next, actually. What would it look like if it wasn't linear?
X squared plus something.
Yeah, maybe x squared plus something, x squared plus 8 maybe. You can't factor that. It's not linear because of the x squared. This would be a nonlinear factor. But x is linear, it's just repeated. Okay. Don't let that exponent make you think it's something else. That's x times x. So, how am I going to set this up? How am I going to set it up? A over x plus 1 plus b over, I'm gonna need an x squared. You could put that next. I like to do them in order though, just like we did over here. From the lowest one, where'd it go? From the lowest one up to the highest one. It doesn't really matter which one comes next, but I need a b over x. Because this is x times x, just like my x minus 1 times x minus 1 over there. And then I need a third one. So you wouldn't have been wrong. We had to put x squared second, but you also have to have the x. This is the repeated linear factor. That's the case 2 that we just talked about. Even x by itself, that's x minus 0, is a linear factor. I want somebody to ask me a question because I see some in your eyes. They're behind your eyes. Yes?
I don't understand how you could put an X in an X squared.
Okay, did you understand why I did an x minus 1 and an x minus 1 squared over here?
Yeah, to get a common denominator.
Right, but before that, before I multiplied by it, why the setup looked like this to begin with? That's the question I'm asking. So when we did this one, the setup, which I brought the equal sign, I had an x minus 1 and an x minus 1 squared. Lloyd, did I erase my problem with the sevens? I did. Let me write it again. Remember the problem with the sevens and it ended up being 8 over 49? This one has a perfect square. The denominator is 7 squared. Right? But it comes from some 7 to the 1s and some 7 to the 2s. And if you start with this, you don't know where it came from. So this x over here is kind of the same idea. It's like my 7 squared. I must have had some 7 to the 1s and some 7 to the 2s. Kind of like that problem. Does that make sense now?
So is it just a placeholder?
Right, because we don't know, maybe we didn't have 2 of them. I mean, for example, if I had 0/7 plus 1/49, I would just get 1/49 and I wouldn't need that one, right? But I don't know if I start here, if I had some of each or not, so we have to have that placeholder just in case there were some of each. Sometimes you will get coefficients that are 0, but sometimes you won't. Like in this case, if I tried to break up 8/49, I would get the 1 and the 1. So you have to have every place from a factor of 1 up to however many factors you have. Tagger, does that feel better now? Other questions? That's the one people miss the most. They just want to put the x squared in there. Then you're missing a whole fraction. Changes everything. Think we're good? Okay, so we have the setup. Nobody else wants to ask a question about the setup? Yes,
And
sir.
that's only because it's a third degree polynomial, or a third degree,
It's because this guy right here was second degree, because that x is repeated. It means x times x. So I have to consider x to the 1 and x to the 2.
okay.
If this had been x to the 3 right here,
You have to have
You'd
that.
have
then
a
I would
d.
have had to have x squared, and I would have had d over x cubed. Everything from 1 up to whatever, however many you have.
Okay.
I'm glad you asked. Anybody else want to ask? Gonna keep the questions behind your eyes? Okay. All right, so we're gonna set that up. What do I need to do? To get the common denominator. The common denominator, lucky for us, is sitting right here. Make sure you reference it. I want to work right to left just because it's easier, I can squeeze it in there. This one over here needs to have an x minus 1 in there to get that common denominator. Right? What's this one need? Another x and an x plus 1. Plus 1? Yeah, plus 1. Right? It needs another x. See if I can squeeze it in here. Another x and an x minus, oops, plus 1. Squeezing it in there. Can you read it? All trying to get that common denominator. Just I call it multiplying by what's missing. What's missing from here, just multiply by whatever's missing.
So C should be x plus 1 also.
Oh, yes. Thank you. Glad you're awake. The sugar's helping. Plus 1, right? I got a little too creative. Did you catch that? I wrote minus 1 the first time. And what about this guy? X squared times x squared times x squared. So first off, you have to know how to set it up. Second, you need to multiply by whatever you need to get the common denominators. Then what?
You can put it all in one.
Put it all into one line. What do you mean all of it?
Like put the numerator all-
Just the numerator figures. Now we're just going to write one long line with just the numerator. So the numerator is going to be 3x squared minus x minus 3 on this side. And over here I'm going to have ax squared plus bx times x plus 1 plus c times x plus 1. I just remember we were going to do that with both ways and we didn't. I forgot. Sebastian, remember you asked me to do it both ways? I only did method 1. Darn it. I'll do method 2 over here and then we'll make it. We okay where that line came from, the numerator? So let's do method 2. Method 2 is where we plug in any values of x we want. Literally anything we want. Some are nicer than others. Anybody have an x they want to plug in there? Negative 1? I like negative 1. Why negative 1? Yeah, it'll make that go to 0. It'll make this one go to 0 also. So let's plug in negative 1. Carefully. Every single x has become a negative 1. And we're not going to lose any. Plug negative 1 into every single x value. many of you will recognize that the reason you chose -1 well, because this term and this term are gonna go to 0. So if you don't write this one or this one, I'm okay with that. I understand that when you chose -1, that's why you did it, because it's all going to 0. If you wanna write it out to see it, that's fine, but if you don't, then I'm okay with that. Those are both gone? I'm left with, let's see, this is a 3 plus 1 minus 3 equals 1A. A equals 1? Okay. We got A. Anything else you want to plug in there? Anything that will make a term go to 0? 0, right? If x equals 0, that'll wipe out a few things. Let me go over there and point to them. You agree if I plug 0 in here, 0 in there? That'd be convenient. So x equals 0 is going to be nice. So now let's let x equals 0. I'm going to write out all of it. You can write out the parts that you want for the -3. A times 0 squared plus b times 0 times 0 plus 1 plus c times 0 plus 1. So I plugged 0 into every single x value in this numerator line that we wrote. Jake, you good? Okay. You're thinking, I saw it. Good for you. So what happens over here? Say that again.
Oh, are you talking about?
Over here on the right? Oh yeah, so this term's gone, right? And this term is gone? Those are both 0? I end up with just -3 on this side. I end up with just c on this side. So I'm feeling pretty good. I've got c and I've got a. Say it one more time, I couldn't
Now,
hear you.
can't you plug in anything you want for X?
I can plug in anything else I want. A lot of people think they're stuck here because there's nothing else that makes things go to 0. -1 and 0 were our only options. But remember, we can plug in any x we want. So we only need one more letter. We could plug in 45 if we wanted. I don't want to do 45 because it's hard for me to square in my head.
You just do one.
I think I'll do 1. But technically, you can plug in anything you want. Choose any x. So I'm going to choose an easy x. We're going to choose x equals 1, and I'm going to plug it in here. And while I plug it in there, I'm also going to put in the a and the c because I know what they are. I know what a and c are, right? So I'm plugging in my 1, and my a and my c. So I have 3 times 1 squared minus 1 minus 3. Didn't I do 1? Oh, we didn't. Very good. Equals, what was a? 1 times 1 squared plus b times 1, b times 1, 1 plus 1, what was c? -3, 1 plus 1, move out of the way here. So I plugged in 1 for all the x's, and I also plugged in my a and my c that I already had found from earlier. You good? Lots of algebra today. Have you seen much trig? Not really. Haven't even gotten to those inverse can yet. Okay. This is 3 minus 1 minus 3. This is 1 plus, that's a 2b, I think. Minus 3 times 2. Agree with my algebra? -1. 1 plus 2b minus 6. 2b minus 5. Combining like terms carefully. Gonna add 5 to both sides. 2b equals 4. B equals 2. Anybody questioning why we chose 1 plug in there? This one right here. This is the most common question I get. Someone will come find me in the office or the lab later, I don't know why we chose 1. We just pick anything, literally. Sometimes you just pick any number. Over here, we chose the numbers that would make things go to 0, the -1 and the 0. Right? But then after that, you can plug anything you want. So, if your favorite number is 5, plug it in there. It'll work. You'll still get B equals 2. Okay, all of that was the algebra, so then now we can do the calculus. We're still not done. We're still not done. So the original problem was, let me bring it over here, so you can see across the room. The original problem was this. 3x squared minus x minus 3 over x plus 1 times x squared dx. We just are going to now rewrite it in the long format as a over the x plus 1. A was 1. B was 2. And C was -3. Is that right? And the match what I have over there? We're ready to do calculus now. Everybody see what I did there? Plugged in the A, B, and C that we just found? Now we can integrate. What's the integral of this guy? Ln of the quantity x plus 1, absolute value, right? And plus
2 ln x.
2 ln x, absolute value of x though, but yes. Do not write ln for that next one. Don't do it. I know you want to. Some of you do. It's not the ln of x squared. Why not? Yeah, because you got an x squared. If it was 1 over x, that's the derivative of ln x. We got an x squared in there. Let's rewrite this term as -3x to the -2. You agree that term looks like this?
It's going to be 3x minus 1.
Yes, we're going to add 1 to this. We'll make it a -1. Divide by that -1. So that's -3 x to the -1 over -1.
3 over x.
3x to the -1, yeah. I just want to make sure everyone sees where it came from. Plus c. Don't get so caught up in doing ln's for everything. Only the linear factors are going to give you those ln's. So the final answer is ln of x plus 1 plus 2 ln of x plus 3 over x plus c. Messy. Questions there? Sasha, you good back there?
Yeah.
Yeah, Evelyn? Yeah? If you had to do this one on your own, could you do it? Probably? That's fairly positive, I like that. Probably. Anyone worried about any piece of it? If you were doing it on your own where you think you might get caught? Okay, so we're gonna move on to case 3. Case 3 has a little note. A little note before we do case 3. And it looks a lot like what I reminded you about when we started today. I reminded you of this integral. There's this little fact that it writes underneath here, which is almost the same, except it's x squared plus a squared. And And the answer looks like this. This little note. How is this one different than that one? How are these different? Besides this one's messier, what makes it messier?
And it has a base squared on.
Yeah, it has an a squared right there instead of a 1. So you remember in the last section we were factoring out anything that didn't have a constant of 1 in it? If you factored out that 1 and then did a u sub, that's what's going on in here. The a gets factored out in the denominator, excuse me, the a squared, right? And then you're gonna end up doing a u sub. You can do a u sub every time, or you can just look at this note and integrate things that look like this as we go. Otherwise, we're spending way too much time doing trig sub on top of partial fractions. But trig sub is where this comes from. Oh, sorry, it's actually u sub. Well, I work trig sub or u sub, both actually. But we need that when we end up with linear factors, which we're about, nonlinear factors, quadratic factors. When you end up with like, Lila said earlier, and I said x squared plus 8 would not be linear, it would be quadratic. That's how we're going to integrate those. So we're going to keep that there when we get ready to integrate a quadratic factor. So case 3 is, what do you do when you have quadratic factors, like my example? All right, so example 3 looks like this. It looks like the integral of 3 over x minus 1 times, oops, I laid myself in that room, x squared plus 2 dx. So this factor is linear. This factor is quadratic and can't be broken down anymore. Everything we've done up till now has been linear factors, only some of them repeated, but we can't break that up anymore. So what you have to do when you have a quadratic is you need to have a numerator that's 1 degree lower than quadratic. Let me tell you what I mean by that. For example, here. This is an x to the 1. Up above here, we have x to the 0, essentially. We put constants, right? So when we call it a, b, or c. This x to the 1, we put x to the 0. This is x to the 1. There's no x's up here, and so forth. But if you have an x squared factor, you have to do 1 degree lower. So a quadratic, what kind of polynomial is 1 degree lower than a quadratic? What do we call them? The quadratic, might be a ax squared plus bx plus c. That's a quadratic. What do we call the ones that are 1 degree lower?
Linear?
Linear. And maybe it would be like ax plus b or mx plus b, right? And then 1 degree lower than that would just be a constant. Constant. It's hard to spell, apparently. Constant. Which maybe just be like a. So when we had linear factors, we were just putting constants above them. Right? We had linear factors, we put constants above them. We had a, b, c's. When you have quadratic factors, you have to put linears above them. I'll show you what I mean. So this guy's linear, so I need an a over x minus 1. But this guy is quadratic. I need to write a linear numerator above that. bx plus c. Just that ugly. That's 1 degree lower than what we have then. So because this is quadratic, this is a linear. And linear might have 2 terms. The good news is those are the only 3 cases we're going to learn today. The The three cases are, if it's just linear factors, no problem, everything's just a constant. If they're repeated, you have, whenever you have repeated factors, you have to have those going all the way up to the highest one from 1. And then if they're quadratic, you need to put a linear above it. I'm gonna put it all together in my next example. Good here? Make sense? Ugly. So now we have to find A, B, and C. Okay. I'm gonna erase my little rationale right here. Common denominator is just this product. So I'm going to multiply this guy here by x minus 1. It's a minus 1 this time. Be careful, make sure you put parentheses appropriately. X minus 1 on that side. And this one's going to get multiplied by x squared plus 2. You can squeeze it in here. X squared plus 2. Fill up more room, sorry. So now I'll have the common denominator. So I'm going to write out my numerator line. Numerator here is just 3. A times x squared plus 2 plus bx plus c times x minus 1. All right. Anybody have an x they want me to plug in? Oh, I like 1 too. 1 also. I like 1 also because it'll make this one go to 0, which makes that whole term go to 0. So I like x equals 1. It's freezing in here all of a sudden. Change that air conditioner. I like x equal 1. I'm doing a little shortcut. That whole thing will be 0. I didn't plug in all my 1s, but can we see that they're all going to 0 there? 3 equals 3a. A equals 1. I think a's been 1 for every example today. Not always 1, just so you know. Okay. Any other x's that'll make things nice? 0? Yeah, I mean, nothing else is going to make a whole term go away, but 0 is at least easy to work with. So at this point, we just need to pick some x's and plug them in. Any x's we want. So Nick wants to plug in 0. Three equals a times 0 squared plus 2. Oops, I know what a is. Let me put it in there. 1 times 0 squared plus 2 plus b times 0 plus c times 0 minus 1. Notice I put the a in there? That's the a right there. This is just 2. This is 0 times b, so this is just c times negative 1. One equals negative c equals negative 1. So I have a, I have c, now what? Plug in something else now, anything. Did you say negative 1? Yeah, I mean, it doesn't really matter. We could plug in 2. I personally would plug in 2 because I would lose a negative sign, but I'll see if I can handle not losing a negative sign. It doesn't matter. We can plug in anything, literally. I'm just saying that I like to plug in positives because I tend to lose my negatives. But I can do it. I just have to be more careful. But technically, we're just plugging in anything we want. And at this point, I'm gonna put the A and the C in there because we know them both. So 3 equals A times, what did we say, -1? -1 squared plus 2 plus B times -1 plus -1 times -1 minus 1. Ooh, there's a lot of -1s there, so I do 2's. Can't keep track of all that. This one and this one are the values that we already found for A and C. Everything else is just plugging -1 in for my x's. Notice I put parentheses around this guy right here? Make sure you do that, because if you don't, you're gonna get -1, it should be +1, it'll change everything. You'll get frustrated if you're not already frustrated. Go right there. So 3 equals 1 times 3 plus, what do we get here? -b minus 1 times -2. We're almost there. We're almost done with the algebra, so we can do some calculus. 3 equals 3 plus 2b plus 2. Distributing my -2 through there. Which gives me that 2b equals -2. So b equals -1. Alrighty then. That was just the busy work to get started, so we can do calculus now. No trig yet though, hasn't been any trig yet. The good news too is it doesn't get any worse than this. It gets messier, but it'll get worse. So I'm going to take the original problem and do what with it? Perfect, put the numbers that we found in for the letters, she says. So put the A, B, and C in and rewrite it like this. So A was 1 over x minus 1 plus -1x, let's see. They're both -1? B and C were both -1 over x squared plus 2 dx integral. I plug my A and my B and my C in. Now we're ready to integrate. Okay, not quite. Now we're almost ready to integrate. Almost ready to integrate. This term right here, we need to break it up into 2 terms. -1x over this, minus 1 over this, because we need 2 different techniques here. So, let's do that. 1 over x minus 1 plus -1x over x squared plus 2 plus -1 over x squared plus 2 dx. What a mess. I swear we're almost there. Everyone see what I broke up there to get the 3 instead of 2 terms? Yeah? Let's just talk about planning. Let's do some planning. Do we know how to integrate this? That's just a natural log, right? What about this?
Sub u.
Yeah, it's a u sub, because if you let the denominator be u, the derivative will be 2x, and we have an x up on top. So this guy's a u sub. We're just planning. What about this last one? way over there on the left.
Is it tangible?
Yeah, it's the inverse tan. Enter the trig. We finally got to the trig for today. That's an x squared plus a squared. 2 is a perfect square. Square root of 2 squared, right? Right, this is square root of 2 squared. So this one's gonna be an inverse tan. We're just planning. What's up, Tigris? Are you talking to yourself or Brittany or both?
I'm just saying like how,
You can't see how it's gonna work yet?
no, I just want to see how like you could recognize that because of the 3 squared.
Because it's x squared plus a constant.
Oh.
Because really what we're saying here is that 2 is a squared.
Oh.
And then what's a have to be? Square root of 2. Right, so no matter what that constant is, you can make it a perfect square. Just make whatever the constant is, make it a squared.
Oh.
Okay, I think we can do it. Let's do the u sub. This one we got. I'm going to do u sub for the middle term. So if u equals x squared plus 2, du is 2x dx. So this one I'm just going to go ahead and integrate. We know how to integrate that guy, right? Easy. Natural log of x minus 1. This one I'm going to write as an integral because we're still working on our u sub there. If du equals 2x dx, I'm going to have to divide by 2. X dx equals 1/2 du. So that's going to be a negative 1/2 times 1 over u du. That's the u sub just for the middle term. There's my u. Here's my du. The negative 1 gets divided by the 2. I'm doing my u sub. And now for this one, let me come over here in the corner again. X squared plus a squared. All we have to do is figure out what a is, and then we can plug into this formula right here. And we just discussed it, that a is the square root of 2. So it's going to be negative 1, so that's my constant, and then times all this. So it's negative 1 times 1 over a, which we said is square root of 2, times the inverse tan of x over a. You guys are looking all the way to the left and all the way to the right. On the far left is the formula that says 1 over a. Remember we said a was square root of 2. 1 over a times the inverse tan of x over a. Let's see. Now we just need to integrate that middle piece and then maybe we can calm down. Maybe. We're good. Enough time. We're good. What's the integral of that middle piece? That's going to be natural log of u, right? So we have to put the u back in there. So here we have natural log of x minus 1 minus 1/2 times the natural log of x squared plus 2 minus 1 over root 2 times the inverse tan x over root 2 plus c. Uh-oh, just cut off my L ending. He's still there. I can't see it. It's too close to the line. L and better now. That's about as messy as you're going to see though. The only thing that might make it messier is sometimes your constants up here are fractions, so like maybe you have a 1/4 right here, and a 1/7 right here, but you're still just carrying around the constant, it doesn't change much. If you were to look this one up in my answer key for the lab assignments, or if you were trying to follow an example online or something, you would see this. These would not be absolute values here, these would be parentheses. Only for that one. Why?
Because any squared will always
Because the
be
square-
positive.
Yeah, anything squared is already positive, you add 2, it's already positive. We don't have to force it to be positive because it is positive, so you don't need the absolute value. I will not mark you wrong if you put them on there, but you don't need them, yes.
Then in that case, a web assignment, will they accept the parentheses, or they accept that?
They'll take either one.
Take either one.
Yeah, website will take either one, but if ever you're checking your work, like, why are they not there? It's almost always because it's already a positive expression. Yes.
Would it be okay if we just always use the absolute value?
Yes,
factor?
better than not using them. Yeah, so you always put them, you'll be fine. It's like if I asked you your age and you said, oh, I'm this. I mean, it's still correct, right? I don't know about your age, but somebody is this age. You don't need the absolute values, but it works. Okay. My very last example is not as ugly as it looks. Okay, maybe it is. But we're not going to do the whole thing. It's just about the setup to make sure you understand all 3 cases. So it actually does have an A through J. But we're not going to solve it. We're just going to set up what the 3 or more fractions will look like. Just so you know, J is the 10th letter of the alphabet, so it might be quite a few fractions. Okay, so case 4 has repeated quadratic and linear factors in it. Actually, no, it only has, look at those have both. Repeated linear and quadratic. And the whole page for you is mostly blank. I actually suggest you set it up sideways almost, because it's that long. Unless you go over 2 pages. It's just to make sure we understand the details. We're not going to do all the calculus part of it because it's too messy. Well, plus just the solving for 10 variables, a little time consuming. We're not even going to solve for them. So notice the directions say set up but do not evaluate. You'll see that on your WebAssign homework too, where it actually wants you to put in the letters A, B, and C and not necessarily find them. It just wants to know sometimes. I mean, other times it will, but sometimes it just wants the setup. So this is a nice messy one. 5x plus 3 on the top. And on my denominator I have x cubed, x plus 1, x squared plus x plus 4, x squared plus 3, the quantity squared. And a little mess of erase. dx. That's all. Again, we're not doing the whole thing, it's just to make sure we understand all the pieces. So first off, do I have any linear factors? How many?
4,
4 linears?
I mean 1.
1? There's 2 linear factors. One of them is repeated, but there are 2 linear factors. This is a linear factor,
And that one's linear factor repeated right next to it.
and this one's a linear factor repeated 3 times, just to torture us. Linear repeated, like the x squared we had before? Repeated 3 times? Yeah? What about this guy? He's a quadratic. Technically, you should try to factor it. If you can, break it up into linears, that would make life easier. But it doesn't factor. So you could try it. It doesn't factor. So this one's a quadratic. And this one is a repeated quadratic. Ew, this sense. Ew. Just helping you recognize it. Okay, we can handle this. Let's work with these factors going left to right. So let's start with the x cubed, just the x cubed. What do I need to do for the x cubed?
so that it.
Beautiful. Jake's up here saying A over X, B over X squared, and C over X cubed. Remember when you have repeated factors, you need everything from 1 up to whatever the exponent is? That's just for this guy. Yeah? What about for him? D over X plus 1. Just one little linear factor by himself. He's so boring now by himself. Yes?
The ordering of them in matters, right?
No. The order does not matter. So if you'd started over here, your letters would be different than mine. Your A might be my D and so forth. But when we solved for them, if your A is the same as my D, and I got A equals 5, you'll get D equals 5. So it doesn't matter, because once you find them, you'll get the same fractions. Order does not matter. I'm just doing them in order so we can follow it here. Okay, so we did this guy, we did this guy, what about him? What goes on top? I heard a lot of mumbling. EX plus F. Right? It has to be a linear expression up top there. Over x squared plus x plus 4. And what about him?
Plus GX plus H over X squared plus
Gx plus h over x squared plus 3.
Yes. We need to do an addition.
And then we need to do it again, because there's 2 of them, right? We have to have it to the 1 and
Plus IX plus J over X squared plus 3.
ix plus j. So because this quadratic factor is repeated, we have to have the quadratic factor to the 1 and the quadratic factor to the 2. And because of the factor is quadratic, we have linears above both of them. We would need like a whole nother day to find all those variables. We're not doing it. We're not doing it. I just wanted to make sure you saw all the little subtleties, what to do with quadratics, what to do with repeated factors. I left out my dx. Yeah, distribute, get the common denominator, no problem. You can do it for fun. And you can't sleep tonight? Work on that. Well, that's how you sleep, right? Questions on any part of that? Okay. So from here, you're going to work on your 7.4? Yeah. 7.4 lab on Tuesdays. The 7.3 and the 7.4 are both due. A lot of you are making a lot of headway with 7.3. I've been talking to you in the lab and so forth. I'm in the lab right now from 3 till 4:15. I'm in the lab tomorrow. You're here tomorrow. I'll be here from 12 to 2. You can also send me emails like a lot of you have been doing.
Well, you'll be here.
I'll be here tomorrow. Tomorrow, 12 to 2.